Welcome to this explainer. Let's just imagine for a second we're sitting together in a grand university lecture hall. I'm going to be your professor today, and we're tackling a question that has literally puzzled physics students for almost 100 years now. Why does nature actively restrict what we can know? Today, we're going to strip away all that complex jargon and dive into one of the most profound truths in the entire universe. Yep, we're talking about the Heisenberg Uncertainty Principle.
Okay, so let's think about a car driving down the street. According to classical physics, the everyday physics we're all used to, we can perfectly track that car. If we set up sensors, we know exactly where its bumper is at any given millisecond, and we can calculate precisely how fast it's traveling down the road. It makes sense, right? We naturally assume that, hey, if we just had better tools, we could do this for anything in the universe, no matter how tiny. But, as we're going to see, the quantum realm absolutely shatters that assumption. So here is our quick roadmap for today's lecture. We're covering 1. The classical illusion. 2. The measurement problem. 3. Wave-particle duality. 4. The mathematics of uncertainty. 5. Einstein's rejection. And finally, 6. A built-in limit.
Let's jump right into section 1, the classical illusion. Now, what's really fascinating here is the sheer scale of the contrast. In quantum mechanics, literally everything has a wave nature associated with its momentum. But for heavy, everyday objects, that wave is basically non-existent. Like, if you toss a baseball up in the air, its wavelength is, well, it's a billionth of a trillionth of a trillionth of a meter. It is so small we completely ignore it, treating the baseball just like a solid object with a definite, predictable path. An electron, on the other hand, is so incredibly tiny that its wave nature becomes its dominant feature, and that makes its exact position highly, highly indefinite.
Moving on to part 2, the measurement problem.
Now, if an electron is that tiny, you might be sitting there thinking, well, why can't we just build a much, much better microscope to measure it? And that brings us to a huge misconception. A lot of people hear about the uncertainty principle and immediately confuse it with the observer effect. The observer effect just means that measuring something alters it, like checking your tire pressure by letting a tiny bit of air out. That's a real thing, sure. But the uncertainty principle, that is something entirely different, and honestly, way more profound.
To be fair, though, even Werner Heisenberg himself initially thought this was just a measurement problem. Back in 1927, he came up with this thought experiment about a gamma-ray microscope. To actually see an electron, you have to bounce a particle of light, a photon, off it. If you use a high-energy photon, you get this super accurate read on the electron's position. But that high-energy photon acts like a cue ball in billiards. It smashes into the electron and completely wrecks your momentum data. On the flip side, if you use a low-energy photon, you don't mess up the momentum. But its long wavelength means you get a terrible blurry measurement of where the electron actually is.
All right, section 3, wave-particle duality.
Here is the absolutely crucial point. While that microscope story is a great way to visualize things, it's actually incomplete. It kind of implies the electron has a definite position and momentum, and our clumsy tools are just getting in the way. But the truth? The true origin of uncertainty is so much deeper. The universe is fundamentally a wave-particle hybrid. Think about a pure wave, like a continuous ripple on a pond. We can perfectly measure its wavelength, which means we know its exact momentum. But where is the wave? It's literally everywhere. It doesn't have one single position. So, to create a wave packet that actually has a localized position, you have to stack up a bunch of different waves with different frequencies. By layering them, they interfere to create a peak in one spot. But because you just mixed all those frequencies together, you've completely scrambled the momentum. The more waves you add to pinpoint the position, the more uncertain the momentum becomes.
Let's look at section 4, the mathematics of uncertainty.
We can actually prove this isn't just a physical guessing game. It's a hard mathematical law driven by Fourier transforms. Notice these two mathematical functions. They're called Gaussian curves. That first graph shows our position function, and it's this narrow, spiky curve. We know exactly where the particle is. But the math dictates that the frequencies needed to build that sharp spike have to spread out super widely. And that gives us the second graph, the momentum curve, broad, wide, and highly uncertain. The math strictly guarantees that the product of their widths can never drop below a specific limit tied to the Planck constant.
To put that into a more everyday perspective, think about photography. Imagine you've got a camera, and you are intensely hyper-focusing on a single, fast-moving subject right in front of you. By forcing that one specific spot into absolute crystal-clear focus, you inherently force the moving background into a heavy, blurry motion blur. You simply can't have infinite sharpness in both places at once. Nature demands a compromise.
Section 5, Einstein's rejection.
Now, if you're sitting there feeling a bit skeptical about reality being this fuzzy and undefined, you're in great company.
Albert Einstein actually rejected this whole idea. He firmly believed the universe was deterministic. He'd argue with his colleague Niels Bohr, basically pointing out that if a speeding car was a quantum particle, under Bohr's rules, it wouldn't even exist in a definite spot until someone looked at it. To Einstein, defying common sense like that meant the quantum rules had to be flawed, or at least incomplete. He famously declared, "God does not play dice."
But Bohr had a brilliant counter-argument. He basically said that our job as scientists isn't to force the universe to fit our everyday macro-scale common sense. Our job is to understand it fundamentally and accept nature's truths, no matter how strange or counterintuitive they feel. The math worked perfectly. The experiments backed it up. Bohr basically told Einstein to stop telling God what to do with his dice.
And that brings us to Section 6, a built-in limit. Let's wrap up with our final conclusion. If there's one thing you take away from our lecture today, let it be this. Uncertainty is not a bug in our microscopes. It's not a failure of human technology. It is a fundamental design feature of a universe governed by probabilities. A particle literally does not possess a perfectly defined position and momentum at the exact same time. The moment you try to pin one down, you force the other into a massive spread of possibilities. It's just baked right into the inescapable fabric of reality. So I want to leave you with this final thought. We spend so much of our lives trying to eliminate uncertainty, right? We want to control every variable, predict every single outcome. But if uncertainty is literally woven into the foundational laws of the universe, maybe absolute control isn't the point. Maybe there's a profound beauty in just embracing the mystery and learning to move forward confidently, even knowing the universe dictates we can never have it all perfectly figured out. Thanks for joining me in the lecture hall today. Keep exploring, and I'll catch you in the next explainer.